In this video lesson, we are going to explore the chemistry of the groups of the periodic table, chemistry of the families, states of matter, allotropes, and a few other odds and ends. Periodic table families. Let's talk about just naming some of the families that have similar properties. Let's start with this right here, not including hydrogen, this group number 1 with lithium, sodium, potassium, and so on and so forth. These are known as the alkali metals. Alkali means base, and when you react these with water, a base, pHs are produced. The second column right here is known as alkali earth metals. These will also react with water, although not quite as spectacularly as the alkali metals. And they also produce a basic solution when you react them with water. This section right here, and even down here, make sure we circle this correctly, right? This section right here, these are the transition elements, sometimes the transition metals. Sometimes this section down here is referred to as the inner transition elements, sometimes the rare earth elements, but nonetheless they are also considered transition elements. Let's see, we have this section right here. This is group number 17. These are known as the halogens. It means salt forming. When you react them with one of the alkali metals, it produces salts. This last group, as you probably already know, is the noble gases. And what we will talk about here, one more thing that I'm going to use a highlighter just to highlight it. Francium, right here, is considered the most reactive metal. Unfortunately, it's not something that you can go purchase because it has such a quick half-life. It doesn't hang around for very long, so we can't really even record it on video. If we're talking about the most reactive non-metal, I'm going to highlight that one here with the element with the highlighter as well. This is fluorine. The most reactive metal was francium. The most reactive non-metal is fluorine. The most reactive non-metal. Okay, that's all we're going to do with that. Let's talk about chemistry of the families. Now, there's really nothing we're not writing in here, but the idea here is that alkali metals have one valence electron. That's this column right here. This is the alkali metals. They are group number 1. They have a +1 ion charge. What you should probably be taking away from this about alkali metals are extremely reactive. You're only going to find them in compounds. They can be extracted from compounds using electricity. But going back to, tied in with this first one, extremely reactive, only found in compounds, they will react violently with water to form hydrogen gas and a base. And we may be able to do this demonstration in class, but it is a bit it's a bit difficult to do since the room doesn't have great ventilation. And then alkali means base, meaning as opposed to an acid. In the second group right here, we have alkaline earth metals. They have 2 valence electrons, so they form a +2 ion. They too are very reactive. They are only found in compounds. We can extract them from compounds using a chemical reaction. They will react quickly with water to form hydrogen and a base, so similar properties, but not as reactive. Okay, not as reactive. So we're going to note that, not as reactive as group 1. Transition metals, there's a range of reactivities. Some are quite reactive, others are not. Some can be found in pure form in nature, like copper metal, silver metal, gold metal. Ions are colored, so compounds with transition elements in them are often colored. This is something that is something you should know about the transition elements. This is groups 3 through 12, so it's quite a lot of elements. That's why there's so much variety in their valence electrons. Their ion charge can range from +1 to +7, right? So many form multiple charges, and you need the stock system to name those that do. The stock system is the Roman numerals. Okay, so that's an important thing to recognize that. If one of the transition metals has more than one possible charge, you have to tell me which one it is using a Roman numeral. Halogens are group 7. They have 7 valence electrons. They tend to form an ion charge of -1. They are extremely reactive and corrosive. They are only found in compounds. You're not going to find them in their elemental form unless humans intentionally make them so, because we can extract them from their compounds using electricity. They will react violently with metals to form halide compounds like sodium chloride. Noble gases, group 18, with 8 valence electrons. They don't form ion charge, so they stay neutral. They are completely non-reactive. They're never found in compounds. Humans can intervene. Xenon and krypton can be forced to react with fluorine in the lab. They have a stable octet naturally, so they don't need to bond. Okay, so those are the important things to take away from that particular chart. All right, let's take a look at the last page of the notes, which is states of matter at room temperature, 25 degrees Celsius. Right, on the classroom table, this is color-coded. Liquids are blue, and there's only 2 elements that are liquids, right? It's bromine and mercury, and if we find them here, bromine is right here, that's going to be a liquid, and mercury right here. Those are the only 2 elements that are naturally liquid at room temperature. On the classroom periodic table, the big giant wall one, those elements will be printed in blue. Gases on the giant wall chart in the room are printed in red. Okay, and so I'm going to highlight those, ironically enough, in yellow, because I don't have a red highlighter. But gases, I'm going to highlight them with this yellow. So that's going to be hydrogen. It's going to be all of the noble gases. It's going to be fluorine, chlorine, oxygen, nitrogen, and that'll do it. Those are the gases. Okay. And then the solids are on the giant wall chart on the periodic table are black, printed in black, and it's basically all the rest of the elements that we haven't highlighted here. Okay. So going back to, I just want to make this note that the liquids, I highlighted them in blue on this chart. They are printed in blue on the periodic table in the classroom. Gases are printed in red, but I've highlighted them here in yellow, and then all the other elements are solids. And this is when you have them at room temperature, because you can take any of these elements and change their state of matter. But natural conditions at 25 degrees Celsius are what are noted here. Allotropes are different physical forms of the same element. Different physical forms of the same element. Couple elements will do this readily. So carbon comes in different forms, the way that they are bonded together. Graphite, the carbons are bonded in flat sheets, which is why they make a great material for using in pencils. Your pencil lead is actually graphite. Charcoal, which is just an amorphous structure of carbons. And diamonds. Diamonds are very strong because the carbons are bonded to other carbons in a covalent bond in all 4 directions. So it becomes a very, very rigid structure. And then there's something called the Buckminster fullerene. Minster, and this is all one word, which is C60. It looks kind of like a soccer ball, and we can maybe look at pictures of that in class. Other elements can do this too. So here's an example, carbon. Another example is oxygen. We can have O2, which is oxygen gas, and we can have O3, which is ozone. Right? Same element, just different physical forms, the way they're bonded together. Other elements that do this are phosphorus and sulfur. And I'm not going to get into details, but the idea here is that different elements, some elements can become allotropes with each other. And we'll just kind of leave it at that as a definition thing. One last thing to kind of, this is sort of a mop-up thing here, but monatomic or diatomic, right? Diatomic molecules, let's start here. Diatomic molecules are when you have two atoms bonded together. If the two atoms are identical, it is what we call a diatomic element. There are only 7 elements that do this. Only 7 elements are diatomic. And we've been abbreviating them as Hofbrinkel, meaning hydrogen, when it's in its elemental form, is H2. Oxygen, when it's in its elemental form, is O2. Fluorine is F2. Bromine is Br2. Iodine is I2. Nitrogen is N2. And chlorine is Cl2. I believe the Rosengarten text rearranges this to say, instead of Hofbrinkel, it reverses it or swaps it to Brinkel-Hof. Either way, whichever way you want to memorize it, those are the 7 elements that are diatomic molecules. Right, so this might seem a little bit contradictory, a monoatomic molecule. This seems like this can't possibly be, because a molecule means you have to have 2 or more atoms bonded together. So how can it be monoatomic if it's a molecule? This is a term that has been used to describe noble gases and noble gases only. It's a Regents term. I'm not going to get too picky about it, but just recognize if you that the Regents terminology, if you're reading anything that has to do with the New York State Regents, working on Regents questions, if you see monatomic molecule, they are just asking you to consider noble gases. All right, that's the last of the notes for the periodic table. We'll see you back in the classroom.